All right. Anyway, we are talking about grammars, specifically context-free grammars, and I don't know if you remember last time I was gonna give you some for you all to try out, but we didn't have the time, so I wanted to start off with that. I hate to just start off with just making you do something out of nowhere. Maybe I'll just refresh our memory about context-free. Oh, hold on. This thing is not. I gotta repair my pencil here. One moment, please. I had to pull the plug. All right, there we go. Replace the plug. All right. Okay, great. The strategies, context-free grammar strategies. These are things that we talked about last time. So first is, if it's a regular language, then you convert from NFA. There's a simple procedure that we talked about how to change an NFA into a grammar. So if the language you're aiming for is regular, then you can always make an NFA for it and then change that into a grammar. If you need balancing, this is the new kind of thing that a context-free grammar can do that a regular language generally cannot do. Balancing, I mean something like A to the N, B, C to the N, something like that. Here we have, what I mean by balancing is, in this example, the number of A's has to be precisely the same as the number of BC's. And the way to do balancing like that is you have to make sure that those two things that you're trying to balance, in this case the A and the BC, they have to be created at the same time in the grammar. So this one, I would do something like S goes to A, S, B, C. This ensures that the A always exactly matches with a BC because I create them at the same time. And I put the S in the middle. That's so that when you do this rule repeatedly, the A's will all begin to stack up on the left side and the BC's will all begin to stack up on the right side. That would not work out if you had done instead A, B, C, S. Then you get A, B, C, A, B, C, A, B, C. If you do this several times, which is not what you want all the A's first and all the B's last. So you stick the thing in the middle to make that happen. Yeah?
If you had like 3 different letters to the end, what would it look like?
This is an excellent question. If you had 3 different letters to the end, it turns out that is impossible to do with a context-free grammar. So you can't do that. But yeah, that's a very insightful question. If it was instead A to then, B to then, C to then, that's impossible. So there are limitations to context-free grammars. All right, so this, just to finish off, this one needs a or epsilon, or else it can never terminate. But that's how you would do, that's a typical sort of easy kind of balancing situation. All right, and then 2 other simple tricks that we talked about were concatenation. To do a concatenation, you do something like S goes to S1, S2, where S1 goes to whatever, and S2 goes to whatever. So this way you can, if you have a language which is made up of strings which look like sort of one thing followed by another thing, you can break it down into a concatenation in this way. Sometimes you got to be sort of smart or cute about how exactly you arrange the S1 and S2. And then a very similar trick is, if the language you're looking at is a union of 2 separate things, that means it can be in this one or this one. And so the trick for doing that is like this. You make a grammar for each of those 2 things, and then you join them together with the vertical bar, which means or. All right. So these are all the simple tricks that we talked about last time. And now I have some examples for you all to try. You can't always use one of those tricks sort of verbatim, but you have to think a little bit outside the box sometimes. But anyway, here is an example. Each one of these, I would like you to come up with a context-free grammar. This is X, XR. That, remember the R here means the reversed. So I will just say, for this one, the alphabet is A and B. That's what I want for all of them. One more. And one last one. This last one, in my opinion, is quite difficult. Last one is all strings that have the same number of A's and B's. All right, see what you think. Feel free to discuss with your friends and neighbors. I would suggest you think of the first one as concatenation. This is the only hint.
Okay.
so you don't need that stuff. This could just be this. Doing okay? That's great. That's awesome. Doing okay? Actually, I like that. This. You can't do that. Not what you want to do, so to get this first part, you're going to do something like that. The way you make those ends is by like doing this rule, the rule itself. Okay? This is good. You want to have something else. How's it going? Yeah, this is good. Okay. This one's good. Because if the S1 is maybe the S2 is but you don't actually want the B's followed by the A's. You just have to end up merged. This is a good idea. But you just take that. That's a good idea. The point is like you want to do this rule to make a bunch of B's. And when you're done with those B's, you can change the S1 to S2. So this here accomplishes no, because of the way the rule works. You remove that S1. So when you do this, you do this rule wherever it's and then this S1 goes to statement mode. And then you do this rule and that. That one is no changes. How we can like this, you should be able to get that from here. Well, no, it's because in this example you have every string here, so like that's the S1 part and that's the S2 part. And you use S1 to create this part, and you use this epsilon rate to make it so it's very covered. And you use this epsilon rate to
So cool.
how's it going? This one, I would say, so this B.
No, Jensen.
Yes, yeah. You have, and they have to because they're. Yeah. How's it going?
I don't know.
Refreshing your memory from last time?
Yeah.
That's a good idea. Yeah, so this one actually is very much like this one. The rest of the second page. Because the one to the squared factor. Something like that.
Also, to make it run, this usually is 4x or epsilon.
Oh, these. I didn't add all these. I bet you checked this out.
Let's take 3 more minutes and then we'll talk about them. I know some of these are a little hard. How's it going?
These look the same.
This is great. Yeah. This one, what's the difference? I would say, think about. They are almost exactly the same. Because this means the string is the same. That means it's first half looks like something, the second half looks like something. Yeah, but almost
You should like, I don't think they play more than
Similar. She said the same thing. She said
it's more like
I can see it.
yeah, the M's.
He said, what am I going to do next year without you?
She was getting anywhere? Yes, that's good.
Jen is on the alley. No, she's mad that you've been hanging out with Jen on. And then you're supposed to hang out with her different.
Do something like a balance where you have S.
You guys had planned hanging out, I guess. That's what she said.
If you start with A and M, that means it has to be A and B because it just
Or I don't remember. She said something along those lines. She said she thinks you're not sharp. She said that to me yesterday. She's a problem. She realized she was probably not.
All right, are we ready to talk about these? I don't think anybody's actually done all of them here. These are a little tricky. There are ones on the homework that are similar to this, so check those out. The homework for today, I mean. But anyway, what about this first one? I think is maybe the easiest one of the lot. This is a fairly traditional concatenation. You think of it as this part and this part, right? And those two parts have nothing to do with each other because those N's on the first part are different from the M on the second part. But anyway, the first part I can do with the traditional balancing, A to the N, B to the N. That's an example we talked about last time. And then the second part is just a bunch of A's. So for that one, I would do something like starting like a concatenation, and where the S1 is the first part, that and the way to make that balancing work out is like this. S1 goes to A, S1B, or epsilon. So that makes equal numbers of A's and B's. All right. So that's the first, that thing in the first box there. And then A to the M, I just need something else for the S2 that just makes a bunch of A's, and the simplest way to do that is like this. S2 goes to A, S2, or epsilon. As I walked around, pretty much everybody said that, so I hope you felt good about that. Any questions about that one? All right, the rest are a little more challenging. The second one is kind of similar, but this one is not a concatenation, not a concat, because you can't break it down into two blocks which have nothing to do with each other. Like you might say, how about this block and this block? But actually, you should not make blocks which separate this B to the M from this B to the 3M, because that has to be the same M. So you cannot sort of split them apart like that. I would say it's more appropriate to interpret this as balancing B's and then with stuff in the middle. by stuff in the middle, I mean that a to the n gets stuck in the middle. But I think of balancing the b's first, and then at the end I put that extra stuff in the middle. So the balancing of the b's would look like this: b, s, b, b, b. That's because I have b to the m at the beginning and 3m at the end. So every one b at the beginning needs to match 3 b's at the end. And then the idea is you do this a bunch of times. That builds up the b's on the beginning and on the end. And then after a while, you stop doing that and you just start making a's in the middle. And so to sort of do this a bunch of times and then transition to doing something else, it will be something like this. So this allows you to do this rule over and over again. And then when you want to, you don't do this rule anymore. You go down to this one and start doing this one now. All right, so this is a typical way to handle a situation like this. And then what should I do for the t? The t, I just want to become a bunch of a's in the middle. So I can do t goes to at or epsilon. So that's how I would solve that one. Any questions about that? It's a little trickier, I guess. Although these are, these things you get used to after seeing them enough times. All right. Okay, how about x reverse? So this one, maybe it would be helpful to just think about what the strings that look like that, what kinds of strings do they look like? They look things like ABBA or AAB, BAA, right? It's one thing followed by the reverse of that same thing. That's what these strings look like. Anybody got an idea for this? I don't
know if this is right, but I did S goes to ASA or BSA or BSB.
ASA or BSB. I like this idea. This is, I think, recognizing the fact that these strings, you'll notice, whatever it starts with has to match what it ends with, right? So if it starts with an A, it's got to also have an A at the end. If it starts with a B, none of the ones I wrote were like that, but something like Bob, right? This one starts with a B and ends with a B. If you want to create a string like that, you can imagine that string growing from the middle outwards, and it can grow according to these two rules, right? You can make any of these strings by using those two rules, growing the string from the middle outwards. I think this is pretty much it. There's one more thing I want to see over here. Anybody feel like something's missing in life? Or epsilon, yeah. This, as written, you can never actually finish the derivation. So I put a little, or epsilon. Yeah, great. That one's a little outside the box. It's still somehow balancing in that if you have an A at the beginning, it has to be balanced by A at the end. And if you have a B at the beginning, it has to be balanced by B at the end. All right. Excellent. What about the next one? X equals X reversed. So this, to me, looks very similar. Actually, those ones that I wrote up there, ABBA, or what else? AA, B, B, AA. Those all work here also, right? Those are strings. These are like palindromes, where the string is the same forwards and backwards. Is there any difference at all then in this one versus the previous one? Any idea? Yeah? Yeah, this is the only difference here. These ones, I can have something like that, where this actually does not fit the format from the previous one because you can't split it. The previous one says you can split it into two parts, where the second part is the reverse of the first part. But that's not true here. It doesn't have two halves, but it still has this still has a property that when you read it backwards, you get the same thing again. All right. So I would say from this one and the previous one, they are almost exactly the same. The only difference is that this one allows some strings which have a single extra letter in the middle. So given that, do you have an idea for it? Really, all you have to do is modify this so that it allows you, if you want to put a single extra letter in the middle. Do you have an idea? Okay. Great. A or B or epsilon. Yeah, so the only difference here is instead of going to epsilon at the end, that, remember, the end in this example represents the middle. So instead of just putting nothing in the middle, you can, if you want to, put a in the middle or a B in the middle or a epsilon in the middle. I like that. This, she wrote it using two non-terminals, the S and the T, although you could have, this is equivalent to just doing this, ASA or BSB or A or B or epsilon. That's the same. This, you don't actually have to do T and then go to another line and make the T do what it do. You can just write this all together. But either way is fine. All right, excellent. And the last one, this one I said was really hard. Maybe as I was looking around, I think people felt like the other ones were pretty hard too. The same number of A's and B's. Anybody got an idea for this one? Maybe want to volunteer their brilliant solution? Same number of A's and B's. My very basic idea for this is to make steps which create the same number of A's and B's every time. Something like S goes to ABS. So if you do this, it is guaranteed you'll always have the same number of A's and B's. Now this cannot make any string with the same number of A's and B's because it's just going to make A followed by B over and over again. But you could also say, or say BS. Now this allows you to make even more stuff. Actually, is that good enough? Or epsilon, of course. Does this, is that good enough to make any string which has the same number of A's and B's? No? Can you think of a string that you can't get? I mean, it's right, yeah. Yeah, this can't make, yeah. B, 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 A, right? Because these rules always make a B right next to an A, and that's not always what you want, right? Can you add more stuff maybe to make this possible? B, 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 A, You got an idea?
Also do BBS and AAS.
I think that's too much. Because if I do BBS, then that's two B's but no A. So then there's no longer the same number of B's and A's. Yeah?
BSA.
BSA, she says, yeah. If you do instead of this stuff, so this was a good attempt perhaps, but you need more stuff. How about also BSA? How about ASB? Might as well, right? Is that going to do it? I think this still doesn't do it. Although now it's complicated enough that I have a hard time at this point deciding if this really is good enough or not. This, I wonder, can it do A, B, B, B? It's not what I meant. Trying to have a cute idea, but it. Can we make this? How about that? Is that possible? Oh, now I have too many B's.
Let's add one more A, or two more A's.
Two more A's. Okay, put them in the middle. I think you can make this. Okay, so maybe this is correct. This might do it. Anybody convinced? I'm not very convinced that this is actually correct, but I included this example just to say some of these are very difficult to do, and furthermore, difficult to convince yourself that you did it right. It's not easy to look at a grammar and answer for yourself if this is really correct or not. My answer for this one, so I will say, well, yes, it can do that. This, can I just say this may be correct? I'm not totally convinced, but might be right. Here's one. This is the answer that I came up with, which I am convinced that this is correct. ASB or BSA or SS or epsilon. Putting SS there allows you to break down the string sort of in blocks. So for example, for this one, forget the previous example because I'm not totally sure if it works. But for this one, let's derive A, B, 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 A, B, A, B, A. How about that? Now the first two rules here are only capable of building basically little, what I was going to say is not correct, but I would think of this in terms of blocks where I can make AB by doing the first rule once, and then I have this block BBA, BAA, and then I have this block here. So I'm going to go S goes to SS first, and then go to SSS. Remember in our book, if I want to be picky about the arrows, they use this double arrow when they're actually writing a specific derivation. And now each of those three S's I'm going to make into one of those blocks that you see above. So the first S goes to ASB, and then SS, and then that first S there now becomes the empty string. So I get ABSS. So now I've made the AB at the beginning, and now we can continue to make the thing in the middle there, BBA, BAA, by doing those first two rules in some order. I'll do the B one first. So this goes to, I had AB there. All right, BSA, S, and then the B1 again, AB, B, BSA, A, S, and then the A1, AB, BBB, no, BBA, S, B, AA, S. I think that's right. This is when I don't want the tour to walk by and just hear me saying B-A, B-B, A-A-A. All right, you paid how much for that? Yeah. And then that first S there can become the empty string. I'm trying to build the string I'm looking for gradually here with an S at the end. And then finally that S at the end can become B-A, and it'll be done. A, B, 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 A, B, A, A, B, S, A, and then that S is the empty string. All right, there you go. So this one example is, in my opinion, quite difficult. Even though, I mean, the language doesn't sound all that complicated. It's all the strings with the same number of A's and B's, but to make a context-free grammar for that, it's not easy, in my opinion. This, I would say, is beyond what I would expect you to be able to do on a test. All right. Any remaining questions about that? We will have some more practice making grammars for various things on the homework that's due tonight, so check it out. All right, great. I had one more thing to say about grammars, and then we can move on to something completely different. And that is, I mentioned once that grammars are used in the real world. Some people have used this kind of grammar to analyze actual human languages with, I would say, mixed success. There's some debate among linguists about whether real spoken languages even have any real grammatical rules at all. We have things that we call rules, but they're not actually, the FBI doesn't come to your house if you violate grammar rules, and people will still understand what you're saying. So they're not real rules in a mathematical sense. But anyway, I did mention that real-life programming languages usually do have specific grammars written out somewhere. And I thought, just for fun, we could look together at the official grammar for the Python programming language. I hope that you can see my screen okay. Is that too small? I don't know. If you just Google for Python full grammar, you'll see the top link is to this full grammar specification. And click on that thing. So this is the official grammar for, I guess, the latest. Is this the latest version of Python? 3.12. And you can see a lot of stuff here. So I thought we would just look at a piece of this. Here's where the grammar begins. They have, so the way that, just because I guess the arrow is a pain to write in a document like this, they use a colon. So this colon right here is what what we would use the arrow for when we're writing the grammar. And then they have the bar, which means the same as what we use the bar for. It means or. I thought it might be fun to just look at sort of a very basic Python statement that you might write. Like, for instance, what if I wrote, can you still see what I'm writing down there? Yeah. How about, this is like real Python. If I wanted a function to square a number, I would say, I'm trying to write it, I'm not sure if this is the best way to write this in Python, but something like this is how I would write it. Return y, right? This is a typical way to write a function in Python. Can we find the little bits and pieces of the grammar which allow you to write lines like this? So this, I looked this up ahead of time. There is something called function definition raw. This is what I wrote, is apparently, here it is. Can you see that? Function def raw. And what it is a function definition looks like, first of all, def. So in Python, when you define a function, it begins with def. So that's def, and then followed by a name. And elsewhere in the grammar, it tells you what exactly a name is allowed to be. But in my case, my name is square. And then you can see some optional things in this grammar with brackets around it are optional. Type parameters, I don't really know what that means. I never write types in my functions in Python. Then the parentheses, the left parentheses. So you can see that right here. That's this. Followed by, in my case, the name of a variable. That's this thing, params. That's a list of parameters. Followed by the right-hand parentheses sign. That's this right here. Followed by some optional business that I am not really familiar with. And then followed by the colon. So this line of the grammar is actually telling you all of the specific little bits that are necessary to make a legal function definition raw. Apparently, a general function definition can be either a function definition raw or decorators followed by a function definition raw. I don't know what decorators are allowed to be, but you can look in the grammar. All right, and then I have, let's just look at the next line is something called, can I scroll sideways? Yeah, block. All right, so what follows the colon is a block. And what is a block? I'm just going to find in the page here. Block. Okay, block consists of new line, that's, here, go to the next line, followed by indent, that's indent, followed by statements. And if you go down to what counts as a statement, it allows things like this with an equal sign in it and so on. And then this thing, dedent, that means, everybody knows in Python, you indent inside of a function, and then at the end you go back. In the grammar, they call that dedent. There's no dedent button on your keyboard, but that's what you do. All right. So would you believe me? I mean, this is a very big and complicated grammar. That's because, there are a lot of things that you could try to write in a Python program, and every possible legal Python line has to fit one of these things in the grammar. So, but the grammar does exist. I mean, nobody really looks at this carefully. If you have a friend who says, "Oh, can you teach me how to write code in Python?" You could say, "Oh, just read through this grammar," and that tells you exactly what's allowed in Python. And this is like the worst. This is technically correct, but a terrible way to learn a programming language. The reason that documents like this exist, though, is because if, for instance, your friend wants to write their own new Python compiler, they will ask you questions like, "Hey, do you really have to have parentheses like this in the definition? Am I allowed to put a space in between this and the parentheses? Could I put 2 spaces if I want to?" All of these questions, a typical programmer will say, "I don't know." But if you want to know, you can look to the grammar, and the grammar will answer all of those questions. Very specific details about what precisely is allowed and what is not allowed, those questions are answered in the grammar. And that's the purpose, that's why the grammar exists. If somebody wants to do something very fancy, like write their own compiler or something like that, you would want to know the grammar. All right, this is all I have to say about the grammar for Python. You can look, if you have other favorite programming languages, You can look up their grammars too. Every typical language has a grammar published somewhere that you can read through. You can read through casually and say, I'm glad I don't actually have to understand any of this, because it's very complicated. All right, any thoughts about that? This is my little show and tell of the Python grammar. Great. Let's move on to something else entirely different then. So that's all I want to say about grammars specifically as another way to generate new languages. I would like to start talking about another kind of machine. This is a new type of machine which can actually generate non-regular languages. That's kind of why we were talking about grammars, is because grammars can make some types of non-regular languages. Here's another type of machine. This is called, we're going to talk about this for the next week or so, stack machine. The stack machine. The stack machine. All right? So this is another machine that, this one we really are going to think of it like a machine, so similar to an NFA or a DFA. Although the stack machine doesn't have states in the same way as NFA and DFA do. But anyway, this is another sort of abstract machine for accepting or rejecting strings. And what is special about the stack machine is it has memory organized in what we call a stack. And if you're a computer science major and you've taken like a data structures class and you learned about stacks, like that's what I'm talking about here. It means the same thing as whatever you think it means, if you think it means something. If you don't think it means anything, then that's fine too. We're going to talk about it. But this is the difference between an NFA, DFA versus a stack machine, is that NFA and DFA don't really have a memory as it goes. It goes through the states, but that's it. The stack machine also has memory, which is organized in a stack. So I'll tell you what a stack means. Actually, before we get to that, let me just say some more sort of basic things here. So as before, or as usual, there is some input string, and you give the string to the machine and it does a bunch of stuff, and then at the end tells you if it's accepted or rejected. There's an input string which is processed just like an NFA, DFA, one letter at a time. And as usual, I'm just going to say left to right. So the machine doesn't look at the entire string at once, just like an NFA or DFA. It just looks, you feed it one letter at a time, and it does something per letter. All right? And each letter, depending on what it is, so according to some rules, or according to what it is, changes the stack. So when you write down sort of an example stack machine, it doesn't look like a state diagram, but it looks like a sequence of rules that says, if you read an A, then this is what happens to the stack. If you read a B, then this is what happens to the stack. And the idea is you read through the whole string, changing the stack each time, and then the string is accepted if the stack is empty at the end. This is a technicality, but that's how this thing works. So if the stack is empty at the end, the string is accepted. And if the stack is not empty, then it's not accepted. All right? But we'll get back to the details of that. This is the overview. Let me tell you about stacks. So what is a stack in, if you've heard about this before, this is, like I said, what you think it is. The stack is basically it's sort of a list. It's like a list or an array in programming, but the thing about a stack is that, let me say, the stack, this is what makes it a stack. It only changes on the top. This is why it's called a stack. It's interacting with a stack is like interacting with a stack of papers or a stack of books or something. You can take the thing off the top, you can put a new thing onto the top, but that's it. There's no way on a stack to, say, grab something from the middle. The only way to do that would be to remove all the things from the top first until you get down to the middle, and then you can take the thing out of the middle. But there are no operations which directly modify the middle of the stack. You can only modify it from the top. And there are, if you think about it, there's only really two things you can do. You can remove the thing from the top, or you can put a new thing onto the top. That's it. Those are the only ways that you can modify a stack. And there are cute little words for that. So here's an example. Let's imagine that I have a stack of stuff like this. And remember, if you're working with this stack, you only can access the thing on the very top in a single step. If you want to get to the B, for instance, you have to first get rid of the D and the C. And there are names for the steps which you are allowed to do. So one step would be to throw away the thing on top, and then it would turn into that. This is referred to as pop. You pop the D. There's a D on top, and I say, I'm going to pop the D. It means you throw away the thing on the top of the stack. All right. And there's another word for putting something onto the top of the stack. Anybody into stacks out there? Remember the other word? Push. Yeah. So the two operations you can do on a stack are pop and push. Pop means you remove something off the top and throw it away. Push. So here, let's say I'm going to push a E. This means you change the stack by adding something onto the top. It's not allowed to do anything except on the top. This is a stack, all right? If you take a data structures class, you'll learn about lots of different things. Like a typical, when you're ordinary programming, like in Python using lists, Python uses lists. And in a Python list, you can actually change the middle of a list or the middle of a string if you want to by using those brackets. But if it's just a stack, then you're not allowed to do that. There's another thing called a queue. Queue, like the British say, like getting in line is like standing in the queue. A queue is one where you can pop something off of one end and push onto the other end. So stuff on a queue sort of, there's a front and a back, and you can remove from the front and add onto the back. That's how a queue works. A stack, you can only remove and add onto the top. All right. And there are other weirder things like that, but these are the main sort of linear type data structures that are used in the real world. Okay. Now, when we write with stacks in this class, I'm never going to draw them like this, just because this is a pain to draw those kind of towers. We're going to write it like this. I would write as DCBA. If you pop the D, now it says CBA. And now if I push E, it now says ECBA. So when we write stacks, the left side is the top. All right, so the top is on the left. And that means whenever we work with stacks, you can only change the left side, not the right-hand side. All right, this is a stack. Excellent. I think maybe we can just sort of do an example of a stack machine. So what a stack machine looks like is just, like I said, it looks like a list of rules that says, when I read this letter, this is how the stack changes. When I read this other letter, this is how the stack changes. So a stack machine describes rules for changing the stack based on the input letter. Right? If I read an A next in the string, then do this to the stack. If I read a B, then do this to the stack. That's the idea. So maybe we'll just do an example here. Just like NFA, DFAs, or anything else, it will take you a while to kind of get used to working with this new type of system here. But this is, a fresh start. If you didn't like grammars, maybe you'll like this. So here's how it looks. Every stack machine, I said, describes rules. And what you're going to see here is just a list of rules. And it's always going to look like read, pop, push. And sometimes I'm going to number the rules just so that they're easy to talk about. There is one typical rule. So what that means is when you read A, if you see S on the stack, you can pop that and then push S followed by X. All right. That's just one rule. So the full stack machine has, several rules. So I'll give them all to you. And then we can talk about BX epsilon. Of course, epsilon, as usual, means the empty string. And there is a read epsilon rule. This is kind of like an epsilon transition in an NFA or DFA, meaning you can do this operation on the stack even without using up one of the letters in the input string. All right? And one last thing that I have to tell you is the stack always, in every stack machine, the stack always begins with just S. All right? This is called the starting symbol. The stack always begins with just S. And like I said before, what it means to be accepted is it's accepted if you can read the whole string and end up with an empty stack. So if we can read the whole string and finish with empty stack, then it's accepted. And if that's not possible to do, then it's not accepted. All right. So let's just try an example. I give you a string. You tell me, is this string accepted or not? So I'm going to, I got a scroll here, so I'm going to try and keep this guy. Oh, I'm going to do this. This is going to be great. Do this. Can you still kind of see that? Yeah. All right. So I would like to know, is AABB accepted? Oh, by the way, I forgot to mention, reminder, tomorrow night is the board game night. Check it out. Where is it going to be? Is it one of these classrooms. 139? That way? Look at the sign. There's signs. Or just walk down this hallway until you see the people. All right. Is AABB accepted? All right. So what we have to do is sort of keep track of this string as we do these various steps to it. So I'm going to write this in a little chart maybe. I have the input string, which we begin with AABB. And then we have the stack, which begins with just S. All right, so this is where we start. And then I'm going to go rule by rule, applying the rule as we go. And the first, remember, you read the input string one letter at a time. So I'm going to read this first A, and it says pop S and push SX. So that means to write my next step, I'm going to kind of cross out that A, meaning I just read this A. I'm reading the first A. And how does the stack change? It used to say S. The first rule says get rid of that S and replace it by SX. So now the stack says SX. All right, and that, if you want to be clear about it, I'm using here rule number 1. All right. Okay, we continue. I think I should do rule number 1 again for the next letter, right? The next letter is another A. So when I do this, I'll cross off the next A because I'm now reading the second A. Can anybody say what will the stack look like now? The rule says pop S, push SX. So you will throw away this S. Yeah? SXX. Yeah. You throw away the first S and replace it with, my old ways again. SXX. Right. You throw away the first S and replace it with SX. So now the stack says SXX. Okay, that was rule number 1 again. All right. Next, I am reading a B. So now you begin to realize some things about stack machines. I hope you can see this all right. I'm going to big it up a little bit more. The next thing that I'm reading is B. Now the B rule says read B, pop X. But actually, you can't pop X in this case. So from this step, it is not allowed to do rule B because the pop is wrong. All right? But actually, we can do rule 3 at this point. Rule 3 is an epsilon read, which means we don't use any letters up. We just do what it says about pop and push. So at this point, maybe I'll just put a little commentary here. Now, rule number 2 can't apply. That's because can't pop X. All right? Because you can't pop X because remember the stack is only allowed to be modified on the left end. And the X's are in the middle. Can't get there. But we can do rule number 3. Rule number 3 has the effect of no reading. So my string is still like that. B is left to read. I'm not exhausting any letters when I do this step. But the rule says pop S, push epsilon, which means the S goes away and it is replaced by nothing. So this was rule number 3. Pop S throws the S away. Push epsilon means you don't put anything back onto the stack. All right? Okay, can we continue from here? I think now you can actually do rule number 2, right? Rule 2 says read B, pop X, and that will actually work here. So I'm going to do rule 2, which will read the next B. This is rule number 2. Reads the next B, and then it says pop X, push epsilon. That is, throw away the X and replace it with nothing. So all that's left is just an X. Can we continue? I think, yes, we can. We can do rule number 2 again, right? Read B, pop X. So now it says A, B, B. Everything has been read, pop X. So we throw this X away and push epsilon here, right? Which means actually the stack is now empty. That was rule number 2 again. Is this string accepted or rejected? It is accepted. Remember, I said the rule is if you can read the whole string and end with an empty stack, then it is accepted. So A, B, B is accepted. Exclamation. I proclaim. A, B, B is accepted. Yes?
If you made another rule that said read epsilon, pop X, and push epsilon, would that accept like all strings?
Maybe. I'm not sure about that exactly. Because if you want to read A's, there has to be an S on the front of the stack. If you do what you said, in this case, if you want to read B's, there has to be an X on the front of the stack. If you want to read some B's, but then after that read some A's, you have to be putting S back onto the stack, which wasn't any of the rules that you said. So yeah, you can. It's good to wonder about, what if I change these rules around a little bit? How would that change the language? I mean, that is what we're going to be talking about, really. Yeah, great. So one little bit of good news maybe, does this look like a pain to write things this way? We are usually not going to write the steps in this way, but I'm trying to be very clear, at least for the first time. But the way that we'll write these, we write the steps in pairs. So if I were to rewrite those same exact steps that you see up there, we're usually not going to make some kind of a big chart like I just did, just because it's kind of a pain to deal with. What we're going to write is more in this style. So each pair, this is the first step, this is where we begin. Each pair indicates the string, comma, the stack, all right? And then this, again, the book uses a brand new kind of arrow for a stack machine derivation. They use that arrow with the little thing on the little tail on the one side. So this arrow is used in the book for stack derivations. And if you want to be very clear, I'm using rule number 1 in the first step. So they would put a little 1 right there. So each arrow is labeled with its rule number. Once you know what you're doing, we tend to leave out the numbers, but if you're trying to be very clear about everything, you can label each individual step. And then the next step we get to, so the way that we're going to write this, I'm not going to write a crossed out A. I'm just going to sort of pretend that A is gone. All right. So what you see in the pair is the portion of the string which remains to be read, followed by the stack. All right. And so in the second pair here, it says ABB. That means I still need to read ABB, and the stack now says SX. So if I were to, let's just write down the whole thing. Next I did rule 1 again, which makes it BB SXX. Next I did rule 2, which pops the S. That was the epsilon read. So now it says BB XX. And now I do rule 3, which is a read B pop X. So that gets rid of a B and it gets rid of a X. And then I do rule 3 again, which is another read B. Sorry, I have my numbers mixed up. I saw confused faces. This should be a 3. This one is 3, sorry, and this one is 2. And then I do 2 one more time, and I get epsilon, epsilon. And what you're looking for when you write it in this way, you want epsilon, epsilon at the end. That's what it takes for the string to be accepted. Remember, accepted means you read the entire string, and the stack says, and the stack is empty. All right? So this is how we will write the steps generally when we're doing these stack derivations. And a pair epsilon, epsilon means accepted. All right? It can be rejected if you get to the end and it's not epsilon, comma, epsilon, or sometimes it can be that you just get stuck in the middle, like none of the rules can apply. That didn't happen in this example, but that can happen. And in that case, also, you say the string is not accepted. So epsilon, comma, epsilon means accepting, and I will say it's rejected if no sequence of rules can reach epsilon, comma, epsilon. Right? Then the string is rejected. This is how we do it. Can we just try another example? Same stack machine, but just another string. See if it's accepted or not. I'm going to copy this again here. Same rules. Let's ask, how about ABAB accepted? All right, so the usual way we're going to write it is like this, right? We begin with the string followed by S, because the stack always begins with S. And then we just try to do our rules one at a time. Which rule should I do first? Rule number 1, yeah. That's the one that has read A. Let's try rule number 1 first. So it says pop S, push SX. So the first A goes away because I read the A. And then the stack part, this S gets thrown away and replaced with SX. So it's like that, BABSX. All right? I don't know if it seemed obvious to you to do rule number 1, but I will point out. Actually, he didn't say this, but you could have done rule 3 at the very beginning, because this is a read epsilon pop s. Can you pop a s? Yeah, you can actually pop s at the very beginning. The problem with that is it empties the stack, and then you won't be able to do anything else. So if you for some reason chose to do that rule first, you would be immediately stuck in the next step. Now that doesn't necessarily mean the string is rejected. It just means you got stuck in the way that the stupid way that you tried to do it was not the right way to do it. So you have to think about, you have to kind of consider all different possible ways that you could have done it to rule out being accepted in any eventuality. Anyway, let's say I choose rule 1 first. I think next we must do rule 3, right? You can't do rule 2. Rule 2 is the only read B rule, but that doesn't apply because we can't pop x in this situation. So we must do rule 3 next. And this will now say, that's an epsilon read, so it's going to be BAB still, but then throw away the s and makes s. Okay. Now the only rule to do, I believe, is rule 2. You can't do rule 1 or 3 because we can't pop s anymore. So we have to do rule 2 in this case. Rule 2 is a read B pop x. So this now says AB comma epsilon. And now from there we're stuck. The stack is empty, and there is no, pop epsilon rule here. So there's no way to proceed from here. Stuck. Now, are we stuck because the string is rejected or because we made bad choices? It is possible that maybe there was some other way that it could have been accepted. Although, what choices did we make? Actually, the only choice we made was in the very first step. So if you want to just be sure, we could have done AB comma S. Rule 3 gives me AB empty string, but then again, we'd be stuck, right? Those are the only real options that we had. And in either case, it gets stuck. And so this string is rejected. It's not possible to get to epsilon comma epsilon. So AB is rejected. All right. Excellent. These, let me just give you you probably will see this terminology in the book. Each pair like this. So these pairs, well, I should say very specifically what it is. These pairs consist of what you see first is the remaining part of the string to be read. Comma, the stack. That's what these pairs look like in each step. And the pairs, our book doesn't call them pairs. They want to be fancy about it. These are called instantaneous descriptions. Because it tells you everything you need to know at a certain instant. So when you begin, it looks like something. Then each step you do, it looks like another thing. And so each of those pairs describes one instant of the stack computation. And these are referred to in the book as IDs, instantaneous descriptions. All right? Yes?
Is it easy to know a string that could be accepted? Because you could pick anything that's rejected, and then you could get epsilon and the state, and then you just take out whatever is left in the left side. Would that be an accepted state?
Yeah, I don't think I've thought about it that way, but I think what you mean is, for instance, when we got stuck here,
yeah.
When you get stuck with epsilon on the stack, I suppose it does mean that the piece of the string that you already read should be accepted. Is that what you're saying?
Yeah.
Yeah, I think that's true. Although I will say, in this particular example, we got stuck in two different ways, and both of those times we were stuck with an empty stack. But there are examples where you can get stuck in a situation when the stack is not empty. And in that case, I don't think you can say the same. If you're stuck but the stack is not empty, then you can't say the stuff that I already read should be accepted because the stack is empty. Yeah, so this is a true fact, I think, but maybe it doesn't come up all that often when you're doing these. All right, can we just say, in this example, the standard sort of usual question that we're going to ask, of course, is what's the language of this stack machine? And of course that means what is the set of all strings which are accepted on the machine? Right, we did AABB and that was accepted. We did ABAB and that was rejected. Did anybody get a feel for this as we're going? What the language, maybe I'll look at the steps again. I'm going to copy this down here. What does it take to be accepted on this stack machine? Anybody got any thoughts? 3 minutes worth of thoughts? What is necessary to be accepted? What do you think?
Is it that there has to be a bunch of A's and a bunch of B's?
Yeah, this is a good idea. I think this is not quite the full answer, but the string definitely needs to have A's at the beginning and B's at the end. That's because, if you recall, the derivation, so the first one that we tested out was AABB and S, right? And the A, you can work with the S. So the first A pops the S and replaces with SX, and then the next A did it again. Right? So you can read as many A's as you like. That has the effect of growing the stack. And then you do this epsilon move to kill the S. And once you do that, I think from now on, everything better be B's or else you're going to get stuck. Because the only rule that you can do without S anymore is rule number 2. So this is what he said. You have to begin with a bunch of A's, and then it has to be all B's. That's true. I think you can actually be a little bit more specific. You got an idea?
Just A to the N, B to the N.
Yeah, it is A to the N, B to the N. The fact is, the number of B's that you're left with here, after you do some A's, the number of B's you have has to actually be the same as the number of A's that you got. That's because each A adds an X onto the stack. And then in order to clear them out and end up with empty, empty, you have to have the same amount of B's as there are X's here. And each X came from an A. So this one, of course you have to get used to this, but in this case, the language of this stack machine is A to the N, B to the N. Which immediately answers, I don't know if you were wondering, can a stack machine make a non-regular language? The answer is yes. This is one. All right, and I think that is enough for